Hello, welcome to the lecture series in quantum mechanics. Today I am going to discuss the expectation value in quantum mechanics. In the last lecture, I have discussed about the physically acceptable wave function, normalization constant, and probability of finding the particles. In this lecture, I am going to discuss the most fundamental concept about the measurement is the expectation value. So let's recall how we measure the expectation value or the average value in classical mechanics. So in classical mechanics, the average is calculating using the definite value of a physical quantity. For example, if the particle have its known position or the velocity, so the average is simply the sum of all the measurement and divided by the total number of measurement. So in classical mechanics, the system have a well definite value all the time, even if before the measurement or even if we don't measure it. But in quantum mechanics, the condition is fundamentally different because uh, particles does not have a single definite value of a physical quantity even before the measurement, and the state can be represented by the wave function psi x. The expectation value in quantum mechanics is the expectation value of a observable quantity represents the average value obtained from large number of measurements performed on a system in a same state, and every observable quantity is associated with a Hermitian operator and its expectation value is calculated using the wave function. So for any wave function, psi x, the expectation value of an operator A is given by expectation value of A is equal to minus infinity to plus infinity psi star x operator A psi x dx and divided by normalization factor. So we can write for the different operators. For the expectation value of x can be written as minus infinity to plus infinity psi star x dx psi x t dx and divided by normalization factor. Here we can see x and psi x are commuted, so we can write like here integrating over minus infinity to plus infinity x mod psi x square dx upon normalization factor. Similarly, we can write expectation value of px. This will be minus infinity to plus infinity psi star x minus I square del by del x psi x dx and divided by normalization factor minus infinity to plus infinity psi star x psi x dx. Similarly, by using the expectation value, we can calculate the different parameters like deviation from mean value. Delta A is equal to operator A minus expectation value of A. Further, the root mean square deviation or the uncertainty also can be calculated by using this formula delta A equal to under root average square average minus average square. Now, this uncertainty delta A will be greater than or equal to 0. These two conditions follow if the wave function psi x is not an eigenstate of the operator A, so the uncertainty delta A greater than or greater than equal to 0. And the uncertainty is equal to 0 if the wave function psi x is an eigenstate of the operator A. By using this formula, let's try to solve some example uh, of the expectation value in the quantum mechanics. So first example is calculate the expectation value of p and p square in a state psi x equal to under root 1 by L sine pi x by L 0 to L. Otherwise, the function will be equal to 0. So let's try to solve this. We know that the formula, this is the expectation value of px minus infinity to plus infinity psi star x minus I h del by del x psi x dx. So first let's normalize this wave function because this is not normalized wave function. So we know that the formula is minus infinity to plus infinity psi star x psi x dx equal to 1. Now if we do psi star psi x, so this 1 by L comes out and mod of a square, this is the normalization constant, and 0 to L sine square pi x by L, here dx equal to 1. So if we use the cos 2 theta formula equal to 1 minus sine square x, now put this value in this integral. So this will be mod of a square by 2L integrating over 0 to L 1 minus cos 2 pi x by L dx equal to 1. Now this will be mod of a square upon 2L square L minus L upon 2 pi sine 2 pi x by L, and limit will be 0 to L. If we put the upper limit, So this will be sine 2 pi, and if we put lower limit, so this will be sine 0. Sine 2 pi will be also 0 and sine pi will be also 0. So this term will be equal to 0. And here length and length will be cancelled out. So this will be mod of a square by 2 is equal to 1. And from this we can calculate the expectation value of the mod of a is equal to root 2. Now let's try to solve the expectation value of px. So this will be minus 2 I h cut by L integrating over 0 to L sine pi x by L d by dx sine pi x by L. This bracket is very important because this differentiation only on the wave function side. So let's try to solve this. So if we differentiate sine x, so this will be cos x. Um, and so this will be minus 2I pi h cut upon L square 0 to L sine pi x by L into cos pi x by L into dx. So we here we can write 2 sine x into cos x is equal to sine 2x. So this integral will be I by h cut by L square 0 to L sine 2 pi x by L dx. Now if we integrate this, so this will be I h cut upon 2L cos 2 pi x by L, and the limit is 0 to L. If we put the upper limit and lower limit, so this will be I h cut by 2L cos 2 pi minus cos 0. So cos 2 pi is 1, cos 0 is also 1. So this 1 and 1 cancel out, and the expectation value of P will be equal to 0. So in this way, we can calculate the expectation value of Px for any wave function. So let's try to solve this by using the shortcut. Here, shortcut is that if any wave function is real or bounded, so the expectation value of P will be equal to 0. So let's see this wave function that is given to here under root 2 by L sine pi x by L. If we recall this, so this is the wave function for infinite potential well, length is 0 to L. So this wave function is bounded only in between 0 to L. So the expectation value of P will be equal to 0. So there are no need to solve this integration or the expectation value of P. We can directly get the answer from here. So let's try to solve the expectation value of P square. We know that the expectation value of P square here we can write in terms of the minus infinity to plus infinity psi star x, and P square will be minus h cut square d square upon dx square psi x dx and divided by normalization factor. So now we can put the wave function here. So this will be minus 2 h cut square by L integrating over 0 to L sine pi x by L and d square upon dx square. This term comes out due to the P square and sine pi x by L. So let's differentiate 2 times by sine x. So it gives also sine x, because if we do one time differentiation it will be cos x, and other this will be sine x. So this integration will be pi square h cut square by L square 0 to L sine square pi x by L dx and divided by normalization factor. Here we can see these two integral are similar. So this gives the same value because both are the definite integration. So this will be cancelled out. And here we can see this is not 0. This is the cancel out, and the expectation value of P will be pi square h cut square by L square. But this expectation value of P square also can be solved directly by using some shortcut. This is valid for the only free particles like infinite potential well, because here the potential energy term will be equal to 0, and we can write P square equal to 2me. So the expectation value of P square equal to 2m into expectation value of E, and we know that the energy for the infinite potential well is En pi square h cut square upon 2ml square. So this is the wave function for the ground state. So n will be equal to 1, and if we put this value, so this will be 2m into pi square h cut square upon 2ml square. Here 2m and 2m is cancel out. This term and this term will be cancel out. So expectation value of P square will be equal to pi square h cut square upon L square. So in this way, we can also calculate by shortcut and or by method. So let's try to solve the other example also. Here, question number 2 is the find uncertainty product, means delta x, delta p for the wave function psi x equal to a e to the power minus x square by 2 lambda square. If we see, this is the wave function for the harmonic oscillator ground state, and this is the Gaussian wave function. So let's uh, solve the uncertainty. Uncertainty means square average minus average square and under root of the total. Similarly, delta p is equal to under root square average minus average square of p. So let's normalize this wave function first. So this is the normalization constant, minus infinity to plus infinity, psi star x psi x dx equal to 1. Now put the wave function. This will be mod of a square minus infinity to plus infinity e to the power x square by lambda square dx equal to 1. Now use this formula. This is the integration over minus infinity to plus infinity x power n e to the power minus alpha times x square dx. So this integration will be gamma function n plus 1 by 2 upon alpha to power n plus 1 by 2. Here we can see in this integral x power n, here n will be equal to 0. So if we put n equal to 0, so this integration will be mod of a square gamma function 1 by 2, because if we put n equal to 0 here, so gamma function will be 1 by 2 and 1 by lambda power 1 by 2 equal to 1. So if we solve this, so we can get mod of a square under root pi times lambda square equal to 1, and the value of the normalization constant mod a will be 1 by pi lambda square power 1 by 4. Now let's try to solve the expectation value of x. If we put the normalization constant, so this will be under root pi times lambda square integrating over minus infinity to plus infinity x e to the power minus x square by lambda square. Here we can, because e to the power x square by 2 lambda square into x power into e to the power minus x square by 2 lambda square. So this will be e to the power minus x square by lambda square. Here if we see, x is the odd wave function and this is the Gaussian wave function and it is the even wave function. So even into odd, so this will be odd function and limit equal and opposite. So the integration of x will be equal to 0. Now the expectation value of p, we can use the shortcut, because we know that if any wave function is real or bounded, so the expectation value of p will be equal to 0. Here we can see, this is the Gaussian wave function and this is the real wave function. Real wave function we can check like psi star x, this will be equal to psi x. So if this condition follow, so we can check the real wave function and the expectation value of px is equal to 0. So in this way, we can calculate two expectation value of x, expectation value of p, both are equal to 0. Now we have to calculate the expectation value of x square and expectation value of p square. So let's try to solve. Here we know that the expectation value of x square we can write here. This is the normalization constant that can be used, and this will be 1 by under root pi times lambda square integrating over minus infinity to plus infinity x square e to the power minus x square by lambda square dx. Now use this integration. Here this integration is minus infinity to plus infinity x power n e to the power minus alpha times x square dx. This will be equal to gamma function n plus 1 by 2 upon alpha to the power n plus 1 by 2. So our integral will be 1 by under root pi times lambda square gamma function 3 by 2 upon 1 by lambda square power 3 by 2. Now if we solve this, because gamma function 3 by 2, so this will be 1 by 2 into root pi, and if we solve this, so we can get lambda square by 2. Similarly, we can calculate the expectation value of p square if we put the wave function. So the formula, in the formula, so this will be minus h square upon under root pi lambda square integrating over minus infinity to plus infinity e to the power minus x square by 2 lambda square d square by dx square e to the power minus x square by 2 lambda square dx. Now let's differentiate it two times. So this will be s square by 2 lambda square upon under root pi times lambda square integrating over minus infinity to plus infinity e to the power minus x square upon 2 lambda square into e to the power minus x square upon 2 lambda square into dx. Now try to solve this. So this integration will be here. This integration will be e to the power minus x square by lambda square. All the term remains the same. Now use this formula, this integration, and if we use this integration, so this will be h square by 2 lambda square. So in this way, we have calculated the four expectation value, means expectation value of x, expectation value of x square, expectation value of p, and expectation value of p square. So let's try to solve the uncertainty product, because we know that the uncertainty in x is equal to under root square average minus average square of x. So this will be equal to 0, and expectation value of x square is equal to lambda square by 2. So this will be lambda by root 2. Similarly, expectation value of p square, expectation value of p square is h square by 2 lambda square, and the expectation value of p will be equal to 0. So uncertainty in p will be under root square average of p minus average square of p. So here we can get the uncertainty in p will be h by root 2 lambda. Now the delta x into delta p will be 1 lambda by root 2 into h by under root 2 lambda. Now if we solve this, we can get delta x delta p is equal to h by 2. This is a very important because for the Gaussian wave function, uncertainty product will be exactly equal to h by 2. For any other wave function, this will be greater than h by 2. So we can solve this by shortcut also for the Gaussian wave function, because we know that uh, for the Gaussian wave function, this is the general form of the wave function fx equal to 1 upon under root 2 pi delta x square exponential minus of x minus expectation value of x whole square divided by 2 times delta x square. So now here delta x is the standard deviation or the uncertainty. Now we can calculate directly. So to find the expectation value of x, compare the given wave function psi x with the above wave function fx. Now to find the delta x, means uncertainty in x directly, so we can compare mod psi square x with the wave function fx. Now here we can see we have given the wave function psi x equal to a e to the power minus x square by 2 lambda square. So we can rewrite this wave function like a e to the power minus x minus 0 whole square by 2 lambda square. Now if we compare this wave function by this fx, we can directly get the value of expectation value of x here. So this will be expectation value of x will be equal to 0. Similarly, to find the value of delta x, means uncertainty of x, compare the mod psi square. So mod psi square will be a e to the power minus x minus 0 whole square divided by lambda square. So if we compare this, so delta x will be here, will be delta x will be lambda by root 2. In this way, we can directly calculate by using this wave function fx in the general form. Now let's recap what I have studied today. So first shortcut I have discussed, that is, if any wave function is real or bounded, so the expectation value of p will be equal to 0. The second one is, this is the general form of the Gaussian wave function fx equal to 1 upon under root 2 pi delta x whole square exponential minus x minus expectation value of x whole square divided by 2 times delta x square. To calculate the expectation value of x, we can compare given wave function by this function fx. Now to find the delta x, means the uncertainty in x, compare the given wave function mod psi square with the wave function fx. In this way we can calculate by using the method and by using the shortcut. This is very important for the competitive exams. So thank you for being with us, and thanks for watching. Please like, share and subscribe.